Hello, in this second lecture on acid-base, we're going to continue where we left off. And in this part, we're going to look at some reasons for why acids are strong or weak, related to why their conjugate bases are very stable or less stable. Okay, so the first reason we're going to use is a pretty logical reason. Most students get this pretty easily. It's related to electronegativity. And we'll extend that to include inductive effects, electron withdrawing or donating effects through sigma bonds. So most students are pretty familiar with the second row elements of fluorine, oxygen, nitrogen, and carbon. And so what we're going to do is we're going to look at the hydrides of those, where we take that particular atom like a fluorine and put a hydrogen on, and then consider that as an acid. So we'll need a base. We're just going to pick a generic base over here. Has the electrons that we need, electron pair donor. We'll stick a minus charge on because all of these acids are weak. And so then we show our typical acid-base equation with base donating to the proton, push the electrons away. So when the electrons are pushed away with that atom, it will also have a minus charge. Okay? So if we donate to HF, we'll make the neutral acid over here, conjugate acid, and fluoride as the conjugate base. Then we could do the same with water. We would make hydroxide as the conjugate base. We could do the same with ammonia, and we would make the amide anion as a conjugate base. And we could even do that with methane and make methyl carbanion right here. So now we would probably expect, I would think most of you could understand this pretty easily, that the minus charge on the fluoride would be the most stable. We would say it has the greatest electronegativity, greatest attraction for electrons, but remember that comes from the higher Z effective in the nucleus. The Z effective on fluorine is +7, whereas on oxygen it's +6, and the Z effective on nitrogen is +5, and the Z effective on carbon is +4. And so that greater positive charge in that Z effective helps stabilize the minus more, so this should be an easier reaction to do. And the HF should be a stronger acid. Now we could test that out by looking at the pKa's. So remember, the pKa is approximately the delta G to ionize this. And so we're looking at a pKa for HF of about 3 kcal. For water it would be 16, so you can see quite a bit difference. Remember, these are exponents that show up in the tens power, the minus of the pKa. And so 10 to the minus 3 is a pretty small number, but compared to 10 to the minus 16, it's enormously large. So fluoride is much better at stabilizing the minus charge. If we compare nitrogen to oxygen, we can see that the nitrogen is much less stable than the oxygen minus, the anion. 10 to the minus 36 compared to 10 to the minus 16. So because of the electronegativity, or the Z effective, the ammonia is a much weaker acid. Pretty straightforward. And then carbon should be the worst, because carbon it's the least electronegative, only has a +4 Z effective, and you can see the Ka is 10 to the minus 50, just basically 0, and the pK is enormous, 50. Remember, delta G is really 1.4 times this, so the delta G for the forming this carbanion would be about 70 kcal. That's an enormous amount of energy. So as we go across, it's pretty straightforward. It's just electronegativity, able to stabilize the minus charge better up here with the fluorine versus the oxygen versus the nitrogen and carbon. Now I want to go back and review a little bit about the inductive effect. We did this in an earlier topic, but I'm just going to repeat it here. If we take a simple carbonyl group with hydrogens on both sides, we know there's a resonance structure where we can push the electrons to the oxygen. And that emphasizes the dipole of this particular bond, positive on carbon and negative on oxygen. So there's a substantial positive, partial positive on this carbon. Okay, and then if we look at its dipole moment, we can see it's 2.3 divi. Now that's a pretty big dipole moment, 2.3, and that's what we're seeing over here. Now what's going to happen when we put this R group in place of the hydrogen? This is actually a methyl, but in more general terms we call it an R group, because it could be other things, anything that's an alkane type group, like an ethyl, isopropyl, propyl, stuff like that. So if I put this here and I draw the resonance structure, Does this help the positive charge or does this hurt the positive charge? Well, the dipole moment should tell us. If the dipole moment gets bigger, it means the oxygen can pull more electron density away from the carbon because this R group here is donating in some to help stabilize it. If the dipole moment gets smaller, then it means the methyl group must be pulling electron density away, making it less stable. Okay, so let's see what we get. It's about 2.7. So what that tells us is that this carbon group is inductively donating electrons in through the sigma bonds. It's like a tug of war. So this carbon's able to pull a little more electron density towards itself when there's an R group versus a hydrogen over here. Okay. Now if that's true, when we come along and put a second R group on there, that should help it even more. If that's the case, then the dipole moment should get even bigger, and we'll see what happens when we go to acetone or propanone. Okay. And what we see is, in fact, it does get bigger. It's about 2.9. So this is a really important idea, is that these R groups are inductively donating. They're almost the only inductively donating group that we have. Almost all of our other groups are inductively withdrawing, at least compared to carbon. So we're going to see this again a lot in Chapter 9. So you want to remember this. So can we explain the dipole moments up here using resonance, inductive effects, or similar effects? So in fact, we do have resonance. We can see that in the second resonance structure here, which emphasizes the positive and a negative. And then we also see the inductive effects as we put on R groups, allowing more and more negative to be directed to the oxygen because the R groups are helping to stabilize the positive charge here. Let's take a look at some other examples. So here's the first two that we just did. We have our reference point over here, just methanol or formaldehyde. And then we added an R group, so methyl group would make this ethanol, or common name acetaldehyde. And then we're going to take a look at what happens if we put a nitrogen here. So this is another case of ambiguity in organic chemistry. The nitrogen is more electronegative than carbon. So a little bit off-center, it's going to pull back away from the oxygen. If I balance that pull of the oxygen with a pull by the nitrogen, that would tend to cancel out part of this, and the dipole moment should go down, should get less. But there's something else here that we should be able to recognize, and that's there's a lone pair next to this pi bond. And the lone pair should allow us to donate in and put more electron density on the oxygen, and that would tend to make the dipole moment greater. So now we have a situation where we can compare inductive effect versus a resonance effect. Okay, the dipole moment should tell us, let's see what we got. Dipole moment goes way up, 3.7. So that would argue that the resonance effect is the bigger influence here over the electronegativity of the nitrogen, inductively withdrawing. Okay, so what we're seeing here is that we have our usual carbonyl resonance with a plus on the carbon, but with the lone pair here we can bring these in and share that, and that allows this oxygen to retain more of the negative charge. So in fact, this is a really powerful effect. Now let's go to an extreme of inductive withdrawal. Put a fluorine here. What does that do? Well, we expect the fluorine to withdraw towards itself, and that should be very strong. If we look over here, nitrogen is less electronegative than oxygen, so oxygen should certainly win in that direction. Over here, fluorine is more electronegative than oxygen, and so the fluorine should withdraw inductively to itself, pull back on that electron density a little bit, and make the dipole moment less. However, we do have a lone pair, like down here, and so we should be able to donate in with resonance from the fluorine. And if that's true, then it should be, like the nitrogen, maybe a little bit bigger than the dipole moment over here. Okay, so what do we see? We see that it actually dropped a little bit. Okay, normally we would think fluorine would really pull electron density back, but it's a competition, so the fluorine is donating in. That makes the dipole moment bigger, but it's inductively withdrawing, and since fluorine is the most electronegative element, it has a very strong inductive effect, stronger than any other atom. So with R groups, remember we're pushing electron density towards the electronegative oxygen. With fluorine, we're pulling electron density away in the sigma bonds. This is a tug of war. And that is balanced by the electron donation in the resonance structures that we see here. Okay, so a lot of stuff on this slide to think about. All right, now let's think about sort of the opposite of acids and accepting electrons. This time, let's look at the conjugate bases and consider them donating their electrons. Okay, so we go across. I have them all mixed up here. Which one would be the best donator? Okay, the one who's most willing to share the electrons should be the best base, the strongest base. And if I go across, I see a nitrogen, a fluorine, an oxygen, a carbon. And so your intuition should tell you that the one that holds on to the electrons the least tightly should be the best at donating or sharing. And when I go across, I'm thinking fluorine's holding the tightest because its Z effective is +7. Oxygen is second, its Z effective is +6. Nitrogen third, Z effective of +5. I think carbon's going to be the most donating with a Z effective of +4. So if we look at how the reaction would occur, remember we're going to use just a generic acid, HA. Donate the electrons, push it away. Notice how our equations never change. The arrow pushing never changes. And then we make the conjugate acids down here. Now we can double check ourselves in terms of which is the strongest base by looking at the Kas or the pKas and finding the weakest acid. Well, we already saw the weakest acid on the previous page, but let's go ahead and put them in here. So remember, the pK is approximately the delta G, and I see over here the biggest pKa, meaning the biggest delta G, to get up to this anion. This is going to be the hardest reaction to do. Coming at it from the other direction, this should be the best base because it lowers its energy the most. Okay, this should be second best, still extremely basic. Okay, that's a very high pKa, so very hard to ionize this. Even water is not what we normally consider an acid, but it's compared to these other guys, it's hugely acidic. And then if we look at HF, it is also technically a weak acid, but compared to water, it's a very strong acid. Okay, so remember, when we go from acid HA, delta G is approximately the pKa times 1.4. So we're going uphill. This is a mountain that we have to climb, and this mountain is the biggest. So this is the weakest acid, therefore this is the strongest base. So I put these on pictures right here. I kind of started up at the energy of the conjugate base, and then what would be the change in energy to go to the conjugate acid. And you can see over here, remember, these are exponents on 10. These are not simple small numbers. So from going from 50 to 45, that's 10 to the 5th. This is 100,000-fold here. So this is enormously different. This one would be second, coming down. Delta G would be, for the acid, would be 37. Coming the other direction would be minus 37. Fluoride is the most stable minus charge, has the smallest drop to the conjugate acid. And hydroxide is pretty basic, but not compared to these two guys up here. Okay, so think about what this picture means. If we were starting down here at the acid, we would have to go up this mountain to get to the conjugate base. If we're starting at the top of the mountain, then we get to come all the way down, whatever this distance is in energy, to reform the acid. Now here's a different series. It has some relationship to what we just said, except now I put an oxygen in here. So we have the H connected to the oxygen in every case across here. Okay, they all have an H on the oxygen. But what I did change was I changed the atom on the other side. So here's a fluorine, a chlorine, a bromine, an iodine. And here's our reference guy right here, water. Right? So I'm wondering, if this is an acid, it's going to donate a proton. So in every case, it would have a base pick up the proton. We'd have two arrows, so we can do that here. So we form this, okay, and we form this. This has a name of hypochlorite, which you might remember from freshman chemistry. If this existed, it's too unstable. We would call it hypofluorite, hypobromite, hypoiodate, and then hydroxide. So what we're saying is, how do these compare in stability to our reference over here? Now if I put an electronegative atom, say I put a chlorine here, is that going to help or is that going to hurt the minus charge? Well, we know that chlorine is electronegative. It's going to pull electron density to itself, and that means it's going to diminish the concentration of negative charge on this oxygen. So the more electronegative our atom is here, the more it can help out the oxygen next door. Hydrogen is the least electronegative of any of these guys. And so all of these guys should be more stable than the hydroxide. The way we could tell is we could look at the pKa's, and if the pKa's are smaller, then these would be more stable, because the mountain that we climbed to get here from the acid is a smaller mountain. We can compare them to each other for the same logic. If we have a smaller mountain, say chlorine is the most electronegative of these guys, and if that's true, it can stabilize the minus the most, and therefore it should have the smallest pKa. We don't really have a pKa for this one because it's unstable, but it should have fit into the pattern. Okay, so we expect the halogens to help stabilize this relative to hydrogen, and we expect the most electronegative halogen to stabilize it the most. Okay, pKa of hypochlorous acid is 7.5. So that is smaller than hypobromous acid or iodous acid. Okay, so just as we expected, now this is not a resonance effect, this is an inductive effect. The halogens are electron withdrawing through the sigma bonds, and that helps stabilize the minus charge on the oxygen. And this is our reference down here. So again, I drew these as pictures so that you can see the energy mountain that we have to climb to get to the conjugate base. And to form hydroxide has the biggest mountain, and the hypochlorite has the smallest mountain right here. Now remember, these are, say, 7.5 to 8.6. That's only one different, but that's in the power of 10. So that's a little more than 10 times different because of the halogen. So let's look at these inductive effects in a little more detail, because an inductive effect can be donating or it can be withdrawing. We've seen that the donating inductive effects come from R groups, like a methyl or an ethyl, or something like that. And inductively withdrawing groups are more electronegative, say, than carbon, like chlorine, bromine, oxygen, nitrogen, things like that. So sometimes each of these effects, donating or withdrawing, can help, and sometimes they can hurt. So let's take a look at two examples. So what would be each substituent's effect, inductive effect, on a positive center, such as a carbocation? Is it going to be stabilizing, destabilizing, or does it have no effect? Okay, our reference point is always the hydrogen here. And then we're going to come along and we're going to put a fluorine in there in place of that hydrogen. Remember, this carbon has not enough electrons. It only has 6 electrons around it, so it needs more electron density. So what did the fluorine do? Is the fluorine going to help this carbon get more electron density, or is it going to hurt this carbon by pulling electron density away? And I think you know from electronegativity that the fluorine is going to pull electron density away. So this should be destabilizing. This withdrawing effect should be destabilizing. That's different than we just saw in the previous slide. On the previous slide we had a minus charge, and the fluorine was good at helping a minus charge. Now if I come along and put an R group here, remember R groups are inductively donating, pushing electrons, so this carbon should be able to push more electrons, and so this should become a more stable carbocation with an R group here, inductively donating. Now what if instead we had a carbanion like this? So again, our reference point is a hydrogen. When we make the changes, are they going to be stabilizing, destabilizing, or no effect? So if I come along and I take this hydrogen, put a methyl here, a methyl is going to push electron density in towards this carbon, which already has too much electron density. So that inductive effect should destabilize this. If I put a fluorine here, I should pull electron density away, which should help spread the excess electron density here throughout these bonds and make this more stable. Be careful because there's no resonance here. To have resonance, you need p orbitals and pi bonds. We don't have any of that here. So in this case right here, the fluorine destabilizes the carbocation, but in this case right here, the fluorine stabilizes the negative charge, and just the opposite for the R group. Okay. So if we look at the arrows, okay, the fluorine's withdrawing, that hurts. The methyl's donating, that helps, positive charge. The methyl's donating, that hurts, the negative charge. The fluorine's withdrawing, that helps, the negative charge. So now let's take a look at another problem. What atom loses the proton here, and why? So if you just guess which atom, it's a guess. Okay, I got 2 hydrogens here, 2 protons. They're equivalent to each other, and then I got 1 here. So I got 2 types. I could have this base come over and take the hydrogen on the oxygen, or I could have the base come over and take the proton on the nitrogen. All right? So you could draw them both out and take a look, but if you consider that the base comes over and takes the proton from the oxygen, I would be left with a minus charge here. And in that case, the minus would be on an oxygen. Compared to if I took this H, the minus would be on a nitrogen. And I think you all know that the minus on the oxygen would be more stable because the oxygen is more electronegative, has a higher Z effective. So we need a couple little arrows there to show us how the reaction works. And then we write the product over here. So you see the minus charge here. Now remember, water by itself, water, H2O, has a pK of 16. So in place of the hydrogen that was here, we put a nitrogen. Nitrogen's electron withdrawing, so it kind of makes sense that the pKa went down, because this minus is a little more stable than if I had a hydrogen here, because the nitrogen's electronegative. Okay, well let's try a different one. So here's a different molecule. It's really a cation. And if we look carefully, we look at the one up here, they look very similar, except I have an extra proton here. So in fact, this pair of electrons was used to pick up a proton. This is the conjugate acid of this guy up here. Now, if we use a base to pick off a proton, we still have two choices. Up here we said making the oxygen minus was the best choice. Down here, I could make the oxygen minus, or I could make the nitrogen neutral. So if I pick off this proton, either of these protons, I would get the molecule up here, which is neutral, and so that should be the better choice. Again, we have our two little arrows, wherever we're going to the proton, and then we have the conjugate base over here, which is the same as this molecule up here. Now, if this is a stronger acid, what should happen to the pKa? If it's a stronger acid, it should be easier to ionize, and that means a lower pKa. So let's take a look and see. pK is 8, so it came down quite a bit, okay, because of the positive charge that's here, going to the neutral structure. The pK is only 8. That difference of 6, so that means 10 to the 6, which is a millionfold. This is a million times more acidic than this one. Let's do one more here. So this time, I just have ammonium ion, all by itself. So instead of the OH here, I have an H. Okay, so that's ammonium ion. I could pick any one of these guys off, so that would be our two little arrows. Now what happens to the pKa? Is this going to be easier or harder? Well, think about it. Up here, I have electronegativity of the oxygen pulling away, and that should weaken this bond, pull the electron density away from the hydrogen a little bit. Or you could come over here and say that the electronegativity of the oxygen helps stabilize or delocalize the lone pair a little bit. Okay, so this should be easier to react up here, meaning a smaller pKa. Now, if that's true, then the pKa of the conjugate of this acid right here should be higher than this pKa here. So there's the conjugate base, and the pKa is higher. It's 9.2. Okay? Now, we'll look at a few more series just to see if we can sort of generalize this a little bit. So first I'm saying, what is or are the acidic protons? So what do we got? We got a proton on oxygen, and we got different types of protons on carbon. So what we're asking ourselves, is the proton on the oxygen more acidic, or is the proton on the carbons more acidic? And I think you would recognize that the proton on oxygen is going to be more acidic, because we're going to leave a minus charge on that atom, in this case an oxygen, way better than a carbon. Okay, but then we have to decide which of these guys is the strongest acid. So just to remind you, if I tried to pull a proton away from carbon, the pK tells me the delta G about 50 kcals. Okay, and if I pull the proton away from water, I get hydroxide 16 kcals. So way, way, way better. Remember, each of these numbers is like a power of 10. Or if you prefer, sometimes I say look at it as like it's dollars. So this little proton here is going to cost me $50,000, and this proton here is going to cost me $16,000. Way easier to put the minus on the oxygen. Okay, so we know we're going to lose the OH in every single case across here. Now, which of these guys is going to be the easiest, have the smallest pKa? So what I see is that 3 of them have chlorine. Okay, we know that chlorine is electron withdrawing, pulling electron density away. If I'm making a minus charge, that should help stabilize the minus by pulling electron density towards the chlorine. This is really our reference point right here, okay, butanoic acid. So whatever it is, it's our reference. Now if I come along and put a chlorine here, I'm thinking pull the minus charge through the sigma bonds towards the chlorine, delocalize it a little bit, and this will be easier. So now the difference is I have a 2-chloro, I have a 4-chloro, and I have a 3-chloro. 1, 2, 3. So which chlorine is going to help the most, or is there a difference? Well, whatever chlorine is the closest is going to have the strongest effect. So I'm thinking this should have the lowest pKa. This should have the second lowest pKa. This should have the third lowest pKa. And this doesn't have a chlorine. It should have the highest pKa. So let's see what the answer tells us. So 2.8, that is the lowest, 4.0, second, 4.5, third, and 4.8, the highest one. So this is pretty close to the typical pK of an alkane acid, of an alkanoic acid. This one's getting pretty far away. Notice the chlorine's 1, 2, 3 carbons down the line. And it's almost the same. So at a certain point, the chlorine effect just disappears. But still, we can feel it a little bit here. Let's take a look at another example. So here, same question. Which is the most acidic proton? And again, as before, we're thinking the OH, okay, should be the most acidic. If I look at all these, they all have halogens except C. C is ethanoic acid, or commonly called acetic acid. Here's our reference point. Any halogens I put on here should pull electron density towards themselves and help stabilize the minus charge. So if I look at the difference, I have 1 chlorine here, I have 2 chlorines here, I have 3 chlorines here, and I have 3 fluorines here. Okay, so we know that 1 chlorine is not as strong at pulling electrons as 2, and 2 is not as strong as 3. So this is going to be the weakest acid, and that'll be followed by this one here with 1 chlorine, this one here with 2 chlorines, and this one here with 3 chlorines. So this should have a lower pKa than any of the other chloroacetic acids. But when I compare these 3 chlorines to 3 fluorines, 3 fluorines are going to be way more electron withdrawing than 3 chlorines, and so this should be the lowest pKa of all. So let's double check ourselves and see. And so we see this is 0.2. This is almost what we would call a strong acid. This is really pretty strong. And second place would be this guy right here, 0.7. It's the pKa, so pretty close to the trifluoro. And then the dichloro, 1.3, a little bit higher. And then the chloro, 2.9. Remember up here it was 2.8, so these are pretty close because they both have 1 chlorine at the first position right there. And then here's our reference one, acetic acid, which is pretty close to the reference one up here, butanoic acid. Okay. So an energy picture here might look like this. For our reference acid, acetic acid, we have to go up 4.7 for delta G, really times 1.4. So, moderate increase, not too bad. But if I put 3 fluorines on there, the climb is almost nothing, 0.2 kcals up, because it has all of those inductive effects withdrawing. So again, sometimes I look at it as money, where every little calorie is $1. So this proton here would cost us $4,700 for acetic acid, but it would only cost us $200 for trifluoroacetic acid. So here's another little series to compare. So these are all alcohols. There is no carbonyl. There is no resonance with 2 oxygens. There's just 1 oxygen. I take this proton away, I have an O minus. Take this proton away, I have an O minus all the way down. So what's the difference? Well, these are all hydrogens. So in fact, this is our reference compound. Or I have 1 R group. Remember, R groups inductively donate, so it's going to be pushing back towards the atom that's going to become negative. Or I have 2 R groups pushing back, or I have 3 R groups pushing back. So how does that affect things? Pushing more electron density in towards the minus of the conjugate base is going to make it harder to form. Okay, higher pKa. And that's what we see. So no methyl groups here, no R groups, 15.5. I put 1 methyl on, it's 15.9. So not a whole lot of difference, but a little bit. if I put 2R groups on right here, so propane 2-ol, it goes up 17, so about from 16 to 17, that's about 10 times less acidic. And then if I put 3R groups on, it goes up to 19. So compared to the 1R group here, that would be 10 to the third, 1,000 times less acidic. Looking at the conjugate base, it would be 1,000 times more basic. Okay, so here's our little methanol guy. That's our reference point. That's the strongest acid, the smallest pKa. And here's our T-butyl alcohol forming T-butoxide. And that's going to be our strongest base or weakest acid over here. Alright, so this is like a totally different topic compared to what we have been looking at. I have all hydrocarbons, so all these hydrogens are equivalent. All these hydrogens are equivalent. All these hydrogens are equivalent. And so any one that I use can serve as our acid. So I pull this proton off, I make the conjugate base. We've already seen that this is a horrible carbanion. Okay, very, very unstable. And then the question is, how do these other ones compare to that? Okay, so if we look at the pKa's, we can tell. pKa of this one is 50, as we pointed out before. Now, if I make this guy here, this is sp2 carbons, it drops quite a bit, 1,000,000 times more acidic, because we changed the hybridization from sp3 to sp2. If we look at this one here, this is an sp carbon, and the pKa is 25, drops to 25. So that's 10 to the 25th times more acidic for this guy. Delta G, remember, is 1.4 times that. But we tend to focus on the pKa's. They're all really weak acids. Okay? 10 to the minus 25 is super weak, but compared to another hydrocarbon acid, it's off the chart stronger. So, excuse me, I think I'm going to have to sneeze. Okay, I guess I'm okay. If we come over here and take a look at the hybridization, what we see is that this one is sp, that's 50% s. The s is the important orbital here for helping stabilize the minus charge. This is 33% s, and this is 25% s. Okay. So what does that do? Well, the more s character you have, the closer the electrons are to the nucleus. Okay, when you fill in the 2 shell, you first fill in the 2s, and then you fill in the 2p, because the 2s is held tighter. And that's what we argue when we talk about oxygen versus nitrogen. Oxygen holds electrons tighter, stabilizes the minus more. And you can see, if you look over here, 50-50, so sp3 carbon is about the same. But if I go to sp2, the pKa goes to about 42 or so. That's pretty close to the nitrogen, 37. And if I look at the sp, it's 25. You know, it's not 16, but it's getting in the ballpark of being close to an oxygen. It's like a very weak oxygen, stabilizing the minus. And so what we argue is that the percent s, as the percent s goes up, the more stable the minus charge is. If we're looking at p orbitals, there is no s, but we don't have that over here. Our percent s is for sp3 is 25, so the least stabilizing for the minus. You can see that here. Or sp2, it's 33% s, so that's middle stabilizing for the minus, and 50% s, that's most stabilizing for the minus. What that's going to turn out to mean is that we can form this one using acid-base chemistry in Chapter 9, and then we will use this in reactions that we study there. And then the triple bond can be modified in several different ways. I just want to point out that this is not resonance. Okay, a lot of times when people see the pi bond, they immediately think, oh, this must be resonance that's causing this. There is no resonance up here because there's no pi bonds. Okay, when we pull it off, it's an sp3 orbital, just like the hydrogens down here are bonded to sp3 orbitals. Everything's tetrahedral. So that's just a reference point. If I have a pi bond here, remember that's perpendicular to the sigma bonds. But when I pull off this proton, that's one of the sigma bonds that we have there. So it's perpendicular to the pi electrons. That means there's no resonance. This is just the electronegativity of the sp2 orbital. Same holds true for the triple bond. I have two pi bonds that are perpendicular to each other, but that's not where the hydrogen is. The hydrogen's perpendicular to both of those, and the electrons are in this orbital here, which is sp. So just again, to remind you, okay, we have the one shell, that the two electrons that shield the +6 nucleus, so we say carbon Z effective is +4. When we fill in electrons into the 2 shell, we fill them into the 2s first, because they're held tighter, just like an oxygen holds electrons tighter. Okay, and then we start to fill into the 2p. So the more s character we have, the more electronegativity orbital, the more stabilizing the minus. Okay, so let's see if we can generalize this. So these atoms that I'm looking at now are not carbon. Let's see, I have looks like this is going to be the acidic site, because I have a positive charge and an extra proton. So in each case, the nitrogen has an extra bond, a fourth bond, and a positive charge. So I'm thinking that's where the acid will be. Now, are they all going to be the same acid strength because they're all NH? Or do they have a difference? Okay, what we saw just above was the greater the percent S character, and hopefully you can see this one has 50% S, this one has 25% S, this one has 33% S. The greater the percent S character, the more electrons are pulled to the nitrogen away from the hydrogen, and this should be a stronger acid. Stronger acid translates into a lower pKa. Let's take a look. So the pK is -10. In fact, this is so strong. This is as strong as hydroiodic acid. This is super strong. If we have an sp2 nitrogen, it's still pretty strong. This would be about like ethanoic acid or acetic acid. Okay, with the sp2 nitrogen. And if it's sp3 nitrogen, this is a pretty typical. Remember, this is the conjugate acid of an amine. An amine would be, say, an NH2. This is a conjugate acid. And the pK is about 9. This is important because you have a lot of amines in your body, and their pKs are in the range of 8, 9, 10. So let's turn this around and look at it in the opposite sense, as a base. Which of these nitrogens is the strongest base? So now remember, a base donates its electrons. So I would donate these, or I would donate these, or I would donate these. Which one of those nitrogens is most willing to donate? So hopefully if you think about it, it's the one that is least electronegative, the one that has the smallest percent S character. So this is sp2, that's 33% S. This is sp3, that's 25% S. This is sp, that's 50% S. So this one should be the most willing to share. This one should be the most basic. sp2 should be second, and sp should be third. The pKs of their conjugate acids will tell us the answer. Remember, these are not the acids. The acids you have to put a proton back on, and then consider how hard is it to pull that proton off. Okay, so let's look at, here's the conjugate acids, and this would be the pKa to make this conjugate base. It requires me to go uphill 5, the pKa. This one would go uphill 9, so it's holding on to its proton the tightest. And this one actually goes downhill. Okay, this one really wants to give that proton away. So this would be the strongest acid, meaning this is the weakest base. Okay, now we're going to look at the other possible explanation, and this has to do with delocalization, which when we get into organic chemistry will be resonance. But initially, I'm just looking at the simple mineral acids, HF, HCl, HBr, and HI. Okay, so I've already written out the equations, and then we'll write what the conjugate base would be. Fluoride, chloride, bromide, or iodide. Now initially, most people guess that HF will be the strongest acid, because F is the most electronegative, and they think, oh, most electronegative should carry the minus the best. But that argument fails here. First off, the Z effective is the same for all of these guys. These are all +7 Z effective. They're in the family of the halogens. What changes as we go down the line is their size. So if we look at a fluoride, radius is about 1.36, and if you figure that as a volume, it's about 10 cubic angstroms. Fluoride has 9 electrons, fluorine, and if we add 1, fluoride, that's 11% increase in electron density, and the package, the volume, is about 10 cubic angstroms. Now if I go to chloride, still a +7 Z effective, it's a bigger atom, And so the volume for the whole atom is going to be about 25, about 2.5 times bigger volume. The increase in electron density is only 17 to 18, and that's only 6% increase. So in fact, there's less electron repulsion here than there is with the small fluoride. Okay, so this is a little bit more stable. Actually, it's a lot more stable. If I go to bromine, it's bigger yet. The volume's about 31, so about 3 times bigger than the fluoride. And the percent increase of electron density is only 35 to 36, only about 3%. Okay, so I have a smaller increase in percent electron density and a bigger package. Bromide should be even more stable. And iodide is the biggest of all. Okay, so its volume is about 4 times bigger than the fluoride. And we only go from 53 to 54, so a little less than 2% increase. And so we're thinking this should be the most stable because less electron-electron repulsion, because it's the biggest space, the most delocalized, biggest volume. Okay, so what tells us the answer? The Ka or the pKa. So here are our acids. Now in fact, HF is what we call a weak acid because it does not dissociate completely. Has a very small pKa, certainly compared to the second row, we just saw that. It's enormously more acidic than water, or than ammonia, or than methane. But compared to its family here, it's the only weak acid. Okay, if we look at HCl, you guys know from freshman chemistry, HCl, HBr, HI are very, very strong acids, 100% dissociate. And they're actually negative pKa's, so that means negative delta G. Very, very favorable. Okay. So now let's see if we can compare some other acids and learn from what we just spoke about above. So here I have H2SE, H2O, H2S, H2Te. These are all in the family, we call these chalcogens. Okay, oxygen, sulfur, selenium, and tellurium. So this is their family, their column. And so what we were just saying is that the ones at the bottom, when you lose a proton, the minus charge is most delocalized and should be the most stable. Okay, we would translate that as to a lower pKa for that particular acid. So looking at our little family here, we'd say Te is the biggest, tellurium, selenium is next, sulfur is next, and oxygen is the smallest. So even though oxygen is the most electronegative, it's the smallest with respect to the argument we're making here. So it should have the highest pKa. The hydrogen telluride should have the lowest pKa. Let's see what they tell us. So in fact, H2Te does have the lowest, 3. H2SE, hydrogen telluride, is about 4, so that's about 10 times less acidic. Hydrogen sulfide, okay, less acidic, and water, the least acidic. Now let's turn it around and look at it from the base point of view. From the base point of view, we're donating electrons, so which one of these two should want to donate the most? Well, whichever one is least stable should be most ready to react, most reactive. Whichever one is most stable should be least reactive. What we just learned was that the bigger the anion, okay, sulfur's in the third row and oxygen's in the second row, the bigger the anion, the more delocalized and the more stable it is. So we're thinking if this is more stable, it should be a weaker base, and hydroxide should be the stronger base. Now we don't actually tell by looking at Kb. What we do is we look at their conjugate acids and compare those. So if I look at the conjugate acids, that would be water, has the pKa of 16, and hydrogen sulfide there has or hydrogen thiolate has a pK of 8. So this is a much stronger acid, meaning this is a much weaker base. Okay, so this hydroxide is much higher above its conjugate acid, water. Okay, let's take a look at another couple. So now I have methoxide against dimethyl amide anion. And so I'm saying which one of these two is going to be the stronger base? Well, we're not comparing a family now. Remember, as we go across carbon, nitrogen, oxygen, and fluorine. So oxygen and nitrogen are right side by side. Nitrogen has a lower Z effective, has a lower electronegativity, more willing to share. Okay, oxygen has a higher Z effective, holds on to its electrons tighter, less willing to share. And so we're thinking that this one should be the stronger base. The way we can tell is look at that conjugate acid. If I put a proton on this, then I have the acid. I can look at the pKa. pK of 37, it's going to require a Hill of 37 kcals approximately to get to this conjugate base, whereas water, or methanol, requires a Hill of 16. So this is going to be much, much more basic. Okay. So remember, here is our patterns. If we go horizontal like this, the one that's most willing to share is the least electronegative. So carbon over nitrogen over oxygen over fluorine. But if we go up and down, the one that is the lowest is the most stable, most delocalized, and that's the least willing to share, whereas the fluoride would be more basic. And then we would look at the pKa's to decide that. So now I've compared a couple of acids here. Both of them have only one kind of hydrogen, ethane and propanone. So can we tell which is the stronger acid in each pair? And what is the basis for your answer? So what we're doing here is we're combining inductive effect or electronegativity effect with resonance effects. So in the first case, if I draw my little acid-base equation, I'd pick off this proton and leave behind a carbanion. I do the same thing here, leave behind a carbanion. But there's a little difference. This one has electronegative oxygen, inductively withdrawing. And if we put a lone pair here, we'd have resonance. So let's take a look. So here's our arrows that we would need. Okay, and these are the two types of structures. So this is pretty horrible structure, minus charge on carbon all by itself. It's basically the worst acid that we could talk about. Whereas this one here, if I pull that proton off, it kind of looks the same, CH2 minus, but this is next to a pi bond. I can push in, and the far atom of that pi bond is an oxygen, and you can see what it does is it increases the acidity of this by 10 to the 30th. 10 to the 30th, whatever that number is. It's so big we don't know. But this one actually becomes a formable carbanion. Even we can form stuff like this approximately in water and biochemical systems. So nature uses this kind of strategy herself to give us some carbons with lone pairs like that. Okay, so the first one, we have a minus on one carbon. And the second one, we have a minus on a carbon and an oxygen. And it drastically changes the acidity. Okay, let's take a look at another one. This time we'll have two types of hydrogen. We have hydrogen on nitrogen, hydrogen on carbon. So I think we could all see that the hydrogen on nitrogen would be much more acidic than carbon, okay, by about 10 to the 13th. Down here I have hydrogen on nitrogen, but again I have the double bond O. So that should greatly accentuate the ability to lose this proton. So what we can do is take a look at the reactions and look at the pKa's. Okay, so if I pick off this proton, it looks like the same as picking off this proton. But when I'm left behind, I have a minus charge on a nitrogen all by itself. So not as bad as the carbanion, but still pretty bad, 10 to the minus 37. The pK would be 37. Notice how much better this one is, because the nitrogen minus can be delocalized to an oxygen minus. And so this is going to be way better than this one right here. And so this will be the stronger acid. This will be the more stable base. This will be the less stable base, the more basic. Okay. This one have minus only on nitrogen, and this one have minus on nitrogen and oxygen. So that helps it out. It's more delocalized. So notice again how this is different than our first example of fluoride, chloride, bromide, iodide. Those are just single atoms that have different sizes. We're changing the size here by making them into resonance systems, where it's spread over multiple atoms that are about the same size. In our last example, we'll use an oxygen as an example. So again, we think the OH is going to be much more acidic than the CH. The OH, again, much more acidic. But in this case, I have a carbon-oxygen double bond here. So I have resonance and inductive withdrawal. So we can show those structures just as the previous ones. We pick off that proton, leave the minus on the oxygen. Pick off the proton, minus on the oxygen. In this case, it's fully localized. It's not bad. Okay, 10 to the minus 16 for Ka. But compared to this one where the minus is spread over two oxygens, it's 10 to the minus 4. So much, much more stable here because of resonance, and there is an inductive effect of the adjacent oxygen. Okay, so we have one oxygen, or we have two oxygens carrying the minus. Two oxygens is way better. So we have resonance effects and inductive effects in our explanations here, and that's what you're trying to be able to use in your arguments. Try and figure that out. Now I put three very important patterns here. Okay, so we got three patterns. We got just sort of an alkane pattern, an aromatic pattern, and a carbonyl pattern. I put X here because that's the atom we're going to manipulate. We're going to switch that out. And the possibilities are CH2, NH, O, and S. So if I just picked any one of them, say this guy right here with these atoms, remember when the acid reacts, we lose this proton and we're left with a minus here. So by now, I would hope that everybody could see that the best minus, if you look at these guys over here, will be the sulfur over the oxygen because the sulfur is more delocalized. They're both in the same family, over the chalcogens. But those guys will be more stable than the nitrogen because of electronegativity and delocalization. And the nitrogen will be much more stable than the carbanion. Okay, so that should be pretty clear. And that's going to be true for all the patterns. So the next question is, how do the patterns relate to each other? Okay, in all cases we expect the one with the sulfur to be the strongest acid when you look at the H's here. So the first one, when we make a minus charge, it's fully localized. Okay, so there's no resonance, it's just the electronegativity of the atoms, or between sulfur and oxygen, the delocalization. In the second case, if we have a lone pair next to the pi bond, we could push into the ring, and we can move that minus around the ring 3 places. Right here, across, and to the bottom here. So the minus is really spread out over 3 different atoms in the ring, plus the X minus. Well, that looks better than this. So I'm thinking that all of these guys, all these X guys here, will be more acidic than the same X over here. And in the last example, if we put a minus on this X, we do have the carbonyl next door, so we can draw a resonance structure with the oxygen minus. That's only one extra resonance structure. But look at the atom that's picking up the minus. Okay, the atom is an oxygen. An oxygen outcompetes carbon hugely. Okay, 10 to the 34th times more stable as a minus. So even though there's only one oxygen here, we're thinking this double resonance right here looks better than this resonance with 4 structures. Okay, well, I have all the possibilities here. So here's up and down. This is the same pattern with a carbon, a nitrogen, an oxygen, and a sulfur. And what we said was that the minus should be more stable as we get more electronegative. Carbon, nitrogen. This is the pK of 50, 37. That's true. This is a huge energy mountain to climb, but it's less than 50. And then if I look at oxygen, that's better than nitrogen by 10 to the 21. And then if I look at sulfur, even though sulfur is not as electronegative, they're both plus 6 Z effective, and the sulfur is more delocalized, so that a greater delocalization is 10 to the 8th times better. Okay, so 10 to the 8th is, what is that? Maybe 100 million. Okay, if we look at the aromatic pattern, okay, forming a minus charge, remember, we can push into the ring 3 additional spots inside the ring. So I have 3 additional spots in every case of carbon, plus I have a 4th carbon, or a nitrogen, or an oxygen, or a sulfur. So we're thinking sulfur should be the most stabilizing. That should have the lowest pKa, 6.5. It does. 10 lower than nitrogen, 28 lower than carbon. So that all looks very logical. Okay. And all of these, if you go left-right, these are all more stable than the left example here, because there's still resonance here. There's 3 additional resonance structures. And over here we said that extra oxygen should really help out. We've already seen this before, so the pKa of a ketone is around 20. But if I put a nitrogen here, it looks pretty much the same, except now I have a nitrogen instead of a carbon. That should be even lower, 20 and 15 it is. And if I look at the oxygen, even lower than the nitrogen, pK of 5, so that's 10 to the 5th times more. And if I put a sulfur there, the sulfur should stabilize it even more. So that's 3.1, about 3. And then if you look left to right, okay, this is 40, but this is 20. So that extra oxygen here outcompetes, all the extra 4 carbon structures here. Okay, so we're looking at differences in horizontal row by electronegativity and the vertical here by charge density. We have resonance structures up here, and we have electronegativity up here, so we have all of our different arguments. So here's 4 acids, and I kind of drew them all related a little bit. They're all 5 carbons long, and what we want to do is we want to predict which acid will be the strongest acid. Okay, so when we look down the line, I see an electronegative atom here. I see none here. I see 2 electronegative atoms, oxygens, and a bunch of fluorines. And I see 2 electronegative oxygens here. Now a base should pick off this proton and leave a minus charge. If I leave a minus charge here with the carbonyl, I should be able to push the minus to the oxygen. If I leave a minus charge here, there's nothing I can do. It's just an alkane carbanion. If I pull this minus off, pull this proton off and leave a minus, I should be able to put it on both oxygens. And I have 6 fluorines, all inductively withdrawing to them. And if I pull this proton off and leave a minus, I should be able to put it on 2 oxygens. So 2 oxygens and 6 fluorines, that should be the best minus. That means this acid should have the lowest pKa. This should be second, this should be third, and this is just a horrible acid. Should have a pK of around 50. Let's take a look. So here's the worst one, 50. We've said that many times. Alkane pKa's are bad, 50. Put on 1 carbonyl, it brings it down about 10 to the 30th. Put on 2 carbonyls, it brings it down another 10 to the 11th. And the 2 carbonyls plus 6 fluorines brings it down another, 4? Another 10,000-fold. So this should be the most acidic, the most stable base, conjugate base. All right. So if we come down here and look at the minus charge that we make, it could be on this oxygen on the right, push all the way back, it could be on the oxygen on the left, and then we have 6 fluorines all inductively withdrawing away, and that makes this into a very, very stable minus charge. Okay. So it has all of our arguments there: inductive effects, resonance, electronegativity. We're going to switch it around just a little bit for our last few slides. Our last few slides, we're going to, instead of looking at acids reacting with a generic base, we're going to look at an organic molecule acting as a base reacting with an acid, because this is an important set of conditions for us. So I have here an amide, very simple amide, ethanamide, and then our acid will be the hydronium ion. So again, once again, we encounter ambiguity. So I have lone pairs on the nitrogen, I have lone pairs on the oxygen. So initially, I think most of us, including myself, would argue that the nitrogen is more willing to share. And so we should push electrons from the nitrogen to the acidic proton and pick a proton up here. But let's take a look. If we look at the pKa, say, of an oxygen acid versus a nitrogen, the oxygen acid is much stronger, meaning the conjugate base is much less basic. So this tells us that the nitrogen base should be much more basic by a lot. But we could also look at the positive charges, so hydronium ion or ammonium ion, and we get the same result. Okay, the oxygen acid is much stronger than the nitrogen acid, so therefore the nitrogen base is much stronger, much more donating. So looking at either of these guys, we're thinking the nitrogen should be the one to donate the electrons. And this is where organic gets really tricky, okay? Because there's something we're not considering. But let's take a look at what we're doing. So what we're going to do is we're going to donate from both of them. We're going to donate from the oxygen, we're going to donate from the nitrogen, and we're going to draw what it is that we form. If I donate from the nitrogen, B, then this is the product that I get. So I have a nitrogen with 4 bonds and a plus charge, which is not bad. I have that right up here. I have NH4+. So that's not a bad thing to draw. But now let's look at the product from using the oxygen lone pair. So if I use the oxygen instead, put the proton here, I have a plus on the oxygen. But remember, this is a carbonyl pi system. We can push the electrons to the oxygen, and I have no plus on the oxygen, it's on the carbon. But remember, the carbon, without any electrons, is next to the nitrogen lone pair, and the nitrogen can donate in and share its electrons. So in fact, if I donate to the oxygen, donate the oxygen lone pair to the proton, I do get a positive nitrogen, and a positive carbon, and a positive oxygen. So in fact, this looks a lot better than this guy up here. So this is not bad, but this is better because of resonance. So what we have to learn is that when we have a carbonyl group, we're always going to push the electrons from the carbonyl group towards the, say, the acidic proton. So here I have another example. This is a carboxylic acid. I have oxygen A, the carbonyl group, and I have oxygen B. So from our example up here, we have to push from the carbonyl group here, okay? Because that'll give us a proton, a positive charge on the oxygen, and then we can write 3 more resonance structures using these other atoms, okay? So it's going to look like that. What if instead I had an ester? Well, it's the same problem. I'm going to push from the oxygen carbonyl, and then I'll have 3 resonance forms. So the point here is if you have a carbonyl group like this, and even if this wasn't here, then you wouldn't even have a choice if it was a ketone. You'd have to push there, or an aldehyde. But you want to make sure you do it that way. Okay, it's a confusing point. Definitely, that's true. But once you see this, you have to remember this, this aspect of it. Okay, we're going to pick just a very few reactions that are coming up in our next topic. I have here a simple alcohol, so you can think of that as organic water. I have a very strong acid, HBr. If I had water and HBr, I would expect 100% dissociation. I expect this to be a base, pick the proton off, and I have sort of the equivalent of H3O+, except one of them's an R group. Okay. Now if I did that, I would have the bromide conjugate base sitting here, and what can happen, what we will see happen, is that this bromide will push off the water. So this will give us a new molecule, a bromoalkane, and then we forget about the water. That's discarded. We call this a substitution reaction. In this case, because the bromide helps to push it off, we're going to call this SN2. But remember, this is our next topic, so I'm just kind of introducing it here. So this would look like this. Notice a couple arrows, that's our acid-base reaction. Then a couple of arrows, that's our SN2 reaction. And this is the important product that we want. Okay, that's an SN2. Now, let me just point out, HBr, Ka is 10 to the 9th. The protonated alcohol, 10 to the 2. So what is the K equilibrium for this first step right here? It's going to be 10 to the 9th over 10 to the 2. So that is 10 to the 7th. Okay. So now let's do the same thing with a secondary alcohol. And here again, you're going to see where there's some confusing aspects that we have to learn. First step is exactly the same. We protonate the alcohol. This is like a water molecule sitting on a carbon. Let's go back up here. In this case here, I couldn't take that water molecule away by itself because I'd have a primary carbocation. But now I can take the water molecule away because the carbon I have here is secondary and I have 2 R groups inductively donating. The bromide can add in, so we get to the same kind of product, but we did it a different way. We did it in multiple steps instead of just pushing off the water. This is going to be called an SN1 reaction. Okay, it's very subtle, but we'll study that more in chapter 9. So this reaction will look like this. Pick up the proton, that's exactly the same. Water leaves, that's different. Carbocation accepts the donation of the electron pair from the bromide. Okay. One more reaction to show, because we have another variation. If we use sulfuric acid and heat, then the alcohol can pick up a proton, just like before. So no difference here in terms of acid-base chemistry. Since this is secondary, the water molecule can leave. We have a carbocation. But instead of the conjugate base of sulfuric acid adding in, the water can pick off a proton and make an alkene, which boils away from the heat of the reaction. So we get an alkene instead of a bromoalkane. Okay, this is called an elimination reaction. So this one would look something like this. We pick up the proton, equilibrium, water leaves, make the carbocation, pick off the adjacent hydrogen here to make a pi bond, and the alkene product. The alkene has a boiling point of minus 48. The alcohol has a boiling point of 83. So if we're heating this up, the alcohol can just sort of sit in there in the warm mixture, and this will just boil away, and we'll get our final product. All right, so that's just about the end of this topic, the acid-base. The stuff at the very end we're going to talk about in Chapter 9, so hopefully it'll make more sense to you then.